This lecture will cover lipids as it relates to our different macromolecules. So ask yourself, what is it that you know about lipids, or fats, maybe more commonly known? These are some pictures of some common lipids for you. Okay, so lipids are a diverse group of molecules, but one of their most common characteristics is they are insoluble in water. We know the saying, they're like oil and water, they just don't mix. So these are going to be comprised of these long nonpolar, which helps you understand why they're non-soluble or insoluble, hydrocarbon chains. So lipids are going to include fats, phospholipids, steroids, and waxes, and we're going to cover all 4 of them. So a triglyceride is a fat. So if you're looking on the back of a nutritional label, sometimes you'll actually see the word triglyceride. That means it's a fat. So a triglyceride has a structure of a glycerol. So you have a glycerol backbone attached to 3 fatty acids. That's why it's tri. Tri means 3. You have 3 fatty acids. Of course, we undergo dehydration synthesis. Does H2O leave, and that's going to bond or build a connection between that glycerol backbone and the fatty acids. So like I mentioned, on the back of a food label, you may commonly see some triglycerides. We're going to cover 2 that are pretty prominent in the triglyceride world. You may have seen a saturated fat or a saturated triglyceride, or an unsaturated triglyceride, and then also there's something known as trans fat, which we won't cover too much, but we'll definitely talk about saturated and unsaturated. So, saturated. Let's talk about this one in more depth. Saturated fatty acids are typically going to form single bonds with each other. We call them saturated because they're actually covered or saturated with hydrogen. So for something to be saturated, it means it's covered. So it's saturated with hydrogens. It has single bonds. And because of those single bonds, they form these very tightly compacted rows, which tend to be solid at room temperature. So again, single bonds. Let's think about what single bonds will look like. You'll have a string of carbons here, string of carbons here, string of carbons here. Very easy to lay these on top of each other and form really tight bonds, such as a solid, right? Think butter. Saturated fatty acids are going to be single bonds, and they're going to form solid at room temperature. You see the triple S that we're building, okay? Saturated fatty acids are going to form single bonds, and they are going to be solid at room temperature. So ask yourself, do you think saturated fatty acids are good for you or bad for you? Think about that. If they form solids, do you think they will be good or bad? The answers are actually bad. So something like a burger or bacon or anything that is full of saturated fats, it tends to form a solid at room temperature. So this can contribute to things like high cholesterol and clogged arteries, which we don't really like. So we want to really limit our intake of saturated fatty acids. So the next one is unsaturated fatty acids. Unsaturated. So let's break this down a little bit. If saturated is single bonds, unsaturated is going to be made up of double bonds, at least one double bond. So what it looks like is you can have some single bonds, but at some point you're going to start to have a double bond. And a double bond causes a little bit of a kink or a bend to form in your chain. So instead of it being straight chains, the chains kind of look like this. If it's just one double bond, we call it monounsaturated. If it's more than one, polyunsaturated. I probably won't ask too many questions on that, but that's for your own knowledge, for understanding, especially dietary needs. So those double bonds form kinks, right? They form these kinks. And those kinks are not going to allow the fat to lay flat. It's going to make the fat kind of bumpy and give it a little more space. And that space is going to allow the fat to be a liquid at room temperature. So unsaturated fats have double bonds, which essentially form these kinks. So they are liquid at room temperature. Very important concepts to understand. Give you a real life example. Think of hair. Most of our African American hair, natural hair, tends to have a lot more volume and a lot more kinks versus you get your hair straightened, it is laying flat. So think about what side of this picture shows saturated fat versus unsaturated fat. I hope you thought to yourself, well, this straight side looks more like my saturated side. Saturated because there are single bonds, and it's going to be basically laying flat or solid in this case. Of course, it's not a liquid, so it can't really be solid, but you're seeing those single bonds allow your hair to lay flat. That's exactly what hair is. Natural hair is kinky. You may have heard of that term. People have more kinks than other in their hair. That's because your natural strands actually do have double bonds in them. So the natural side is going to be more like unsaturated fat, in which there are double bonds present, and it allows it to have more kinks. That's why your hair doesn't lay flat to your head. It's going to do whatever, depending on if you got a good hair day or a bad hair day. So hair is a great example of something like straight hair kind of mirroring the saturated or the single bond style, while something that is a kinkier hair texture is going to be more like your unsaturated fat with more double bonds. Okay. Another type of lipid is a phospholipid. So a phospholipid contains a glycerol backbone, boom, and you also have two fatty acids, but this time you have a phosphate group. So instead of 3 fatty acids, you have 2 plus this phosphate group. Because of this, you now have 2 different sides to your molecule. You have a polar side, which, as you can kind of guess, will like water, and a non-polar side, which will hate water. So that's going to cause this phospholipid to be amphipathic. We talked about that. We said that's going to be something that has both sides. That's what a phospholipid will be. So a phospholipid is going to have a polar head. So it's going to have a polar head, and then it's going to have these non-polar tails. So you got a polar head and non-polar tails. The non-polar tails hate water. The polar head loves water. What happens is our phospholipids actually make up our cell membrane. That's good because one side of the cell membrane is going to have the polar heads as it interacts with things like your bloodstream or liquid in your body. And then the non-polar tails are going to face inward. So you end up forming this phospholipid bilayer. Phospholipid bilayer, in which you have polar head, non-polar tails, and they're going to orient themselves where the heads are on the top, and then the tails are faced inward. Same thing here, it forms this phospholipid bilayer, 2 layers. The other type of lipid is a steroid. I know that's crazy. You probably didn't think a steroid was a lipid, but it is. It has a very different structure than other fats. You see it's more of a ring-like structure. It doesn't have the long tails, but a steroid is a fat. And really small differences in steroid structure can lead to big changes. So I'm going to tell you some of our steroids because most of the hormones in your body are actually steroids. So things like estradiol, testosterone, progesterone, cortisol, estrogen that's not up here, those are examples of steroids, and we know how hormones work. We know how the production of testosterone can lead to really big changes on a young male, right? They might get more facial hair, get a broader chest, all those type of things as a result of this teeny tiny steroid being produced or hormone being produced. And then our final type of lipid is a wax. So waxes are extremely hydrophobic, meaning they hate water. And that's good because they have a purpose to kind of repel water. So something like earwax is designed so that you don't have a lot of liquid to enter your ear canal. So you want it to be very resistant to water. Beeswax and even cuticle wax. So something like a plant has this little cuticle wax on its surface. That's to try to help limit the amount of water from escaping. So we want our plants to be well watered, but if they're in a hot environment without any type of protective coat, then now all of that water we put in will evaporate. So we put that wax over it. And again, those waxes are just going to be long structures that are going to be useful. So these are just examples of waxes. Okay, so that's all we have for waxes. The waxes was pretty short. The next video we'll talk about proteins and nucleic acids.